Good afternoon. I would like to start with two small announcements or reminders. The first is that the course evaluation is going on for ETH students. I mentioned that last time. The deadline is noon on in 2 days, I think, or in 3 days. So please fill that out. As I mentioned last time, I would be extremely grateful to get your feedback. Then the other information that is probably already reached you is that the written exam will take place on January the 25th. At least the ETH students have been notified of that, but the same exam date will also apply to university students who would like to take the exam. It will be in the morning between 8:30 and 11:30. It's quite early, but I think there's a lack of rooms, in particular in current times where they need more space. So I'm sorry for this maybe not optimal timing. Okay, so then let us start or continue where we stopped last time. Maybe the end of the last lecture was not completely satisfactory, because what I did last time was to tell you that we have now reached the Einstein-Hilbert equations, or reached the level where we can write down the Einstein-Hilbert equations. And that by itself is, of course, a nice thing to do. Let me remind you how they look like. They have this Einstein tensor, Gij, so it's a 0,2 tensor, components are Gij, and then the cosmological constant times the small g, which is the metric, equal to 8 pi Gn, which is the Newton constant. So that has nothing to do with this Einstein tensor here. It's just a constant, and which we, by the way, can set to 1, as you know. And if we set it to 1, we can measure length in terms of mass. And then we have the energy momentum tensor, which we introduced last week. And that was the reason why we finally were able to write down this equation. Now, the obvious question that arises is, where does this equation really come from? And that is a topic that we will address today, or a question that we will address. There is no unique answer. The situation is a bit similar to Maxwell's equations. Maybe if you remember how Maxwell's equations were derived, maybe you don't remember how they were derived historically, but how it was done in the lectures, then it was probably a mix between experimental facts, like the Coulomb law that can really be determined from direct observations, combined with certain, let's say, theoretical principles. These are usually some symmetry principles, that things should look the same when you move and so on, as well as maybe other experimental facts that were added to that and so on. So there was an interplay between experiment and theoretical research. Now, in the case of gravity, what was clearly already known experimentally was Newton's law of gravity. And whatever this theory that Einstein wanted to develop would look like, it had to reproduce Newton's laws of gravity as a special case. So in that sense, there was an experimental input, and this experimental input was already kind of worked into a formula, namely Newton's law of gravity, which was known to be true in a certain limit. And then, of course, Einstein added certain principles, as you know, the equivalence principle, as well as other principles that is, for example, just already the idea that gravity should be represented by geometry. And from, again, by an interplay between, let's say, trying to find the right principles and trying to make or come up with a theory that has the right, in the right limit, the correct behavior, correct, I mean, the known behavior, the known experimental behavior, Newton's law of gravity, he at some point came up with this equation here. So in that sense, you can regard this equation just as a postulate. Of course, it was difficult to derive, but it's a postulate, and then we can verify this postulate and see, for example, that indeed it reconstructs or leads to Newton's law in the appropriate special cases. And if you think about it, this is something you can do relatively easily, because we already know that the Schwarzschild solution is a solution to these equations, And you also have seen that in the Schwarzschild solution, as long as we are sufficiently far away from the center, the laws are very similar to Newton's laws of gravity. For example, there was this geodesic deviation, which exactly corresponded to the one of Newton's gravity. Still, there are certain parts in this equation which needed further experiments. And one part was this. This was a part that just had to be added because, or I mean, it had to, Einstein added it because he realized that without this term, the overall equation, so if you set this term to zero, or the constant to zero, the cosmological constant to zero, then the equation will not lead to static solutions. And Einstein was convinced that at the end, the universe is something static. So he tried to somehow supplement the equations with additional terms that would still fit or be consistent with the general principles, but allow him to argue that there could be a static solution. Now it turned out, and there was a long discussion, that this solution will not be stable, actually. So it's kind of a static solution, but not a stable one. So it was, in that sense, not a very good reason to introduce this term, because the universe would, after a slight, let's say, perturbation, suddenly still go into a non-static regime. However, the solutions without this constant was a solution which would just say that the universe expands. And it was indeed later realized experimentally, and this was Hubble's discovery, that the universe is indeed expanding. So then one arrived at the conclusion that maybe this constant is not needed. And Einstein even admitted that it was an error to introduce this constant. Nowadays, we have a situation that we are in the situation that we have even better experimental astronomical data, and we know that the universe is not only expanding, but it's expanding in an accelerated manner. And in order to retrieve that, you again need that constant, and need it not to be zero. So today, the view is essentially that the equation requires the constant, and determining the value of the constant is a matter of experiment at the end, of course, in astronomy. Or you may ask whether it could also be determined by tabletop experiments, but maybe we'll discuss later that this constant is so small, or the effect of this term is so small on small scales, that it would be extremely difficult to see an observable effect. Okay, so that's where we are. Now it's still, if you compare it again to Maxwell's equations, we know that Maxwell's equations could also be derived from in a way, nicer postulate, namely from an action principle. And the same is true for Einstein's field equations. And that's what I would like to present in the following hour or 1.5 hours. I would like to show that we can derive the Einstein field equations from another postulate. We still require a postulate, but the postulate is in many ways nicer and maybe gives more insight into the structure. And I will explain in the course of this derivation, or maybe at the end, why this is the case. But let's just start and do it, and then maybe the discussion will be more concrete once we have done the derivation, rather than if I now make a long introduction to why this is so useful. So I think the usefulness will become quite apparent. So let me just start with a definition, which is the Einstein-Hilbert action. The Einstein-Hilbert action is something you could express as a function which takes as input the metric on a manifold. So that's the metric. Obviously, that's always what G is. And this U is a compact submanifold of space-time. So just call it submanifold. And compact will be useful if we later want to consider boundary terms. But that is something I will not explain in more detail for the moment. Let's just assume we have some region, some domain U, and now we can define on that domain, or we can essentially assign to any such domain U for any given metric G a number. And this number is given by, first of all, a prefactor, which is essentially just a convenience. So you see, whenever there's a prefactor appearing, I could as well have absorbed it into the constants of nature. So you see that already here. There's always a 8 pi in front of the Newton constant. And so, of course, the Newton constant was there before Einstein's relativity theory, but maybe if Einstein was first, we would have just integrated this into Gn and not write this 8 pi. In this case, we would just have a factor of 1/2 here or 1/2 Gn. And otherwise, nothing would change. So this prefactor is in that sense not of any significance, the convention. Then we take an integral, and the integral is just over the Ricci scalar. Let me write this again, because it's essentially almost the only thing that enters here. And then the volume form omega g. So you know any metric defines a volume form, and if you want to integrate, we need a volume form. We call this the canonical volume form. So far, this is just the definition. But now there's a claim. This is the important claim that will now concern us for the next hour or so. The claim is that the vacuum, and we will even make a stronger claim, but for the moment, the claim is that the vacuum equations. So, of course, I'm always talking about the Einstein field equations, and by vacuum equations, I now mean the equations where we set the right-hand side to 0, and let's for the moment also set the cosmological constant to 0. This will not come out of that, because obviously we would have to input it somewhere. The vacuum equations are just delta, or the variance. So I vary this action with respect to G. Maybe I'll write this as a little G here. And require that this gives 0. I will just in a minute explain what the variation means in this case. But the idea is that the Einstein equations are now expressed in a simpler form, if you like. So the form is simpler in the sense that, you know, in this formulation here, you have somehow, you can count how many equations do we actually have. It's a bit like in Maxwell's equation. There are many equations here. We have this Einstein tensor. It has in total 16 components, but it's a symmetric tensor, so there are only 10 independent components, but we essentially have 10 different equations. Also remember that this G itself is composed of the Ricci tensor minus the Ricci scalar times the metric. So this is itself a rather complicated object. This is only the Ricci scalar. So the claim is kind of really in some way a nice one. I mean, at least it smells as if there is something deeper to be understood, because it tells us this equation, which may look still in a way arbitrary, it has this G. Why does G have this form of being Rij minus 1/2 times R times Gij? You remember, hopefully, this definition. It just says, just integrate over, I mean, drop this constant for the moment, just integrate over the Ricci scalar and try to minimize this integral. And the metric that will minimize this integral is the Einstein, or will be a solution of the Einstein field equation. Or expressed differently, minimizing or extremizing this will exactly give the Einstein field equation. So we just vary it, so this means we vary the metric a little bit and see how the whole thing changes. And of course, if it doesn't change with small variations, this means we are either at a minimum, a maximum, or potentially a saddle point. So it's this law that is important. It's not whether it's a minimum or maximum. The important thing is that if we vary it a bit, it shouldn't change. But of course, you can think of it as an extremum, if you like. Of course, you are familiar with that. At least in classical mechanics, you should have seen variational principles to derive the Hamilton equations or the equations of motion in general. And it's remarkable that the same procedure works in general relativity. Let me make a few remarks about what this variation really means. So when I say that this variation is zero, I think I could equivalently write something like this. And it will also require additional explanations, but let's define something like a derivative with respect to a function, or in this case, even a tensor field. G is, of course, a tensor field. So it's essentially a function that assigns to each point of the manifold a tensor. And in that sense, it's a variation with respect to a function. So let's take this derivative to a function of SU. And then, so this is like a derivative of the function, and then again multiply it with a variation of G. And this should give 0 for all G's. Now, you may feel like this expression that I wrote down is a bit strange because it has these symbols delta over delta G, and here again the multiplication with delta G. It will not be part of this lecture to introduce this formalism in full detail. However, I would like to just present an analogy to something you know extremely well. And the analogy will essentially really be a one-to-one analogy. You could even, I mean, it's more than an analogy, you could even think of it as a special case that you know already well. And you will just have to believe me that even though you only know the special case well, all the laws and rules you know about the calculus in this special case also apply in the general case. If you want to do that more rigorously, I would just refer to the corresponding mathematics lectures. So this should be done either in differential geometry or in an advanced analysis course, or also maybe partially in classical mechanics, where variational calculus is, of course, also a topic. But I will not repeat that here. But I will now tell you what rules we need to know. So in order to understand the analogy, think of just an arbitrary. So think first of this object here. So it's something that takes as input the function. It's in that sense a functional, as it's sometimes called. And let's now just take a general functional capital F, which takes as input the function. So this I will call a functional. And this is now a function that it takes as an input. And of course, this is just a special case. So here the functional is S. Obviously, you see S is well assigned a number to any function G, if you like, small g. And here the generic identifier that I use for the function is just phi. So phi is a function that is given as input to the functional f. Now let's take the special case. Let's consider the special case where the function phi is not, as in our case, a function on the manifold, but let's suppose it's just a function that only takes a discrete set of inputs. So let's suppose it's a function that takes a value, let's say an entire number between 1 and some big number n, or some number n, and maps it to the reals. Now, if I have such a function, I would say, okay, the function takes as input such a number. I may just call it small t. So small t would just be the input to the function phi. It's an element from this set. But we are kind of used that if a function takes as input a value which is discrete, like in this case, we would just actually write it as for example, something like this phi with a little index t. And indeed, that makes sense because you can just think of the function as a vector or as an n-tuple. So the function is completely defined. So it's defined, or is it, I mean, really actually equivalent to by the tuple phi I until phi n. So no, they are not n functions. It's really the little index is now the input. So they're just n numbers. that are given as, excuse me. No, that's correct. So the function f is completely defined by that. It's essentially telling us that if I now want to evaluate phi, for example, for the value t, I don't need to write this again. It's already here. If I want to evaluate the function for an input t, I just take the corresponding entry in this n tuple. Now why do I do all that? If you look at this special case, then it's really just normal multivariable analysis that is going on. And so that's something you probably understand extremely well. And therefore, we can just now also understand the rules of the variation rules that are going to be useful for today's lecture. So when I now write f of phi, so if I apply the functional, then of course f just needs to take as input everything that defines the function, which is just this tuple here that I just mentioned. So that's equivalent because the function is completely described by this tuple. Now what does it mean if I write something like delta f to delta phi, which is what I wrote before in the case of the action S? What does that now mean in this analogy? So this really just means in the analogy that it's essentially the gradient of f. It's just, I mean, maybe a picture could also help. So if I have here t, and here is phi of t, then what we actually have is just a discrete function. Maybe I'll put it like this. So rather than a continuous function, we have a discrete one. And taking the gradient just means that I essentially take the derivative with respect to changing the function only for argument 1, and then so on. So what this of course means is that it's just d to the dx, or d, excuse me, it's d to the d phi 1 of the function until d to the d phi n of the functional. So the functional is now a multivariable function. Of course, so the reason why we are even looking at now different notation is that, of course, we are not interested in a discrete function, one which only takes discrete value. For us, the function phi will itself be a function on the reals or even on the manifold. And in this case, if we would use this notation, there would be infinitely many inputs, not even countably many, because for any real number t, I would need to provide an input and vary the function there. Nonetheless, as I mentioned before, all the rules that we know from calculus, from multivariable calculus, still apply in this more general case. And this is actually something that is relatively straightforward to verify. It's a bit cumbersome. We really have to first define what is exactly the class of functions and so on. Otherwise, you get certain problems or certain continuity problems and so on. But in principle, it's just that. So, by the way, when I write something like that, the delta phi, or the derivative of the functional to the phi, and then times delta phi, then what this means is essentially that I have defined something like a little vector delta phi 1 until or a tuple delta phi 1 until delta phi n. And I just take the product of that. So I take this times delta phi 1 and so on. And add all those f and then delta phi n. So that gives a meaning to this term. And that's important that you know this meaning, because that's what I wrote essentially here. So that's exactly analogous to that. Okay, so that's essentially what I wanted to tell you, that if you see such a thing, in order to make sense of it, translate it into such an expression, and then you essentially know what it is. Of course, I could also write this in terms of gradients. This would just be delta phi as a gradient, and then scalar product with delta phi, which is also an n-tuple. Okay, so I really hope this analogy helps. Now, once we have the analogy, and the reason why I introduced it is that we will actually need to apply certain rules. So we will have some expressions as follows. For example, we may have a product between functionals. And now the question is, how do we deal with that? Now, once you know that everything translates into this, of course, all the rules about derivations apply, as I said before, in particular the product rule, for example. So we can therefore say it must be true that this is also, this could be written like this. So it's just the statement that the product rule applies, which I write down here explicitly for once. And similarly, for example, the chain rule, which also works. So if I have a nested functional, I can also apply just the rule that I need to take the exterior derivative times the interior derivative, and so on. So from now on, I will just use this new type of derivative of functionals exactly the same way as I would use normal derivatives. Not sure, there was some noise. Was there a question?
I don't think it was a question. There is one question in the chat.
Okay, what is it?
Is it the right intuition that the Ricci scalar is the integrand because it represents the energy and momentum density of vacuum space-time?
Oh, let me just see. Yeah, I wouldn't say so. So the question is, the Ricci scalar essentially represents energy momentum density. No, we are now in the vacuum case, and so in that sense, we would have at least no energy momentum even from vacuum. You may now maybe view it in principle as an energy density of the gravitational field itself, but that is a bit dangerous and would be require a longer discussion. But what it certainly is not, it doesn't have to do anything with the matter. So it doesn't have anything to do with the energy momentum tensor that we introduced. You may, if you are careful, maybe somehow related to some property of the, some energetic property of the gravitational field. But I would prefer not going into that, because actually assigning energies to the geometry is a notoriously difficult business. I may come back to the difficulty itself when we discuss the information paradox next week, but let's not do that. Okay, now we have essentially the tools, or at least the notation, to first of all understand what this claim means. So I hope it's clear what this means, and also to prove it. So let's just prove it. This will be kind of, okay, not very difficult, but yeah, still quite tiring calculation. And I have to admit, I'm not very good with signs, so it may well be that I will make some sign errors, so please pay attention to the signs and tell me if I make an error there or any other error with the indices. But let's try to really go through this calculation. It's kind of an important calculation, and despite the fact that I said it's tiring, I want to do it, also because, I mean, yeah, you probably see the significance of it. It's almost obvious. It's really the calculation that essentially derives the Einstein field equations from a nice postulate, namely the fact that this Einstein-Hilbert action is the correct action principle. Okay, so let's start with the calculation. So what we need to do is to essentially vary this thing. So that was given. So the right-hand side will just be 0. So let's write down explicitly what that thing is. So what we vary is really this action that I introduced. And the action that you see still on the first slide can now be written more explicitly in terms of the Ricci tensor, Rij times Gij. I mean, at some point I need to use the definition of the Ricci scalar, and the Ricci scalar is defined exactly in that way, that it's this product that I just wrote between R and G. So we'll have to use that at some point. And then we have the metric, and the volume form. And maybe you remember that the volume form is the square root of the determinant of G. That's something we did earlier on. So now I just wrote the action in coordinates. So I'm assuming here implicitly that there are coordinates. Okay, now I made the assumption explicit. And actually the assumption that I'm really making here is that this integration area is sufficiently small so that everything fits into one chart. But again, that can easily be generalized. I'm not doing that, it's a bit cumbersome, but we know there's this decomposition of unity, and then we can write the whole thing. We could write it as an addition of several integrals over individual charts, and so on and so forth. But let's for the moment make that assumption to simplify our task a bit. And I don't think we would gain any insights by looking at cases where the chart doesn't cover all of you. Okay, now I told you before that, okay, maybe because I told you that, let me even write it more explicitly. I told you that we will take this derivative to the metric, delta to the delta G, and that it satisfies all the rules. And one of the rules, as I mentioned, is of course the product rule. So let's just apply the product rule. So if we apply the product rule, one thing I have to do is of course to take the derivative of one part of this thing, and for reason, I mean, just for to group things a bit, to group the calculation, I will still take the product between Gij and the determinant of G together as one big factor. And so we integrate over that one. And then I will write a completely different integral. I just separated in order to have a cleaner treatment later. I will write an extra term for the whole rest, which is again an integration over U, where I apply, which consists of the first part that comes out of the product rule, delta to the delta G of Rij, and of course it still has this Gij with which it is multiplied, and the determinant of G and dx to the 4. Now our next task is essentially evaluate these brackets. So we need to find out what this means, and we will need to find out what this means here. Let's give these terms some numbers. So let's just say the whole first term is 1 and the whole second is 2. And let's start with 1. And please feel free to interrupt me at any point of this calculation. I will try to go relatively slowly through it, but there are certain points I will just, or certain steps I will just make, assuming you are aware why I can make them and not go into details, but then you can just slow me down and ask. So to evaluate 1, we first need to establish something, which I just make as a remark, namely that the determinant of G, which is what this whole thing here means. So this is just an abbreviation for the determinant of G and then the absolute value of that. The determinant of G can be written as an exponential of the trace of the logarithm of G. Okay. Do you know this expression? Okay, that's maybe something I could briefly show in case there is a desire that I show that. You may have seen that in linear algebra. So who wants me to briefly show why this is the case? You can maybe press yes. Okay, so yes moves faster. So let me briefly do that. Let me just do it here in another color. It's kind of a side remark, because that's really something that has nothing to do in general with GR or differential geometry. It's a matrix theoretic statement. So first note that the expression is independent of the basis choice. Which means that if I mean, this is just a general property, by the way, of functions of matrices. So you can think of, if we talk about the determinant, then of course we think of G as a matrix. Now, a function of a matrix, like the logarithm of the matrix, is actually defined by going into the diagonal basis and then take the logarithm of the diagonal values there. So therefore, the definition is basis independent, because it's part of the definition to say we go into that basis. And so I can therefore just say I'll evaluate the whole thing. So we choose, let's evaluate it in the diagonal basis. So again, the reason is these functions of matrices are basis independent, and also the trace. That's something you know from linear algebra. If I change basis, the trace doesn't change. And then, of course, here, the last thing is just an exponent of a trace, but this is an exponent of a number. This is anyway basis independent. Now, if I'm in a diagonal basis, then the whole thing looks actually very nice. It's just the trace of the logarithm of the matrix with the diagonal entries. If I'm d-dimensional, it looks like this. Of course, in space-time, I would start with zeros, but because this is now a general linear algebra statement, let me just write it like that. And then you see that if I take the exponent of first of all, the logarithm just means I apply it to the individual components or to the diagonal values. So I just have the logarithm now inside of the matrix. And now taking the trace of the matrix, of course, leads to ln G11 and so on, plus ln G dd. And now you see that this is, they're just normal exponentiation rules that tell you now that if I take the exponent of a sum, or excuse me, if I take the exponent of a sum, this just gives a product, but the exponent of the logarithms gives again G, the G entries, so I just get G11 times G22 and so on until G dd, which is of course the determinant of G. And the determinant is itself, again, basis independent, and therefore we have established the claim. Okay. Now, why do we need this expression here? This expression is useful when we vary. So let's just do that. So what I want to do is to really calculate this, the variation of the determinant of G with respect to G. Now, if you look at this expression and now apply the chain rule for derivatives, which I said also applies, then you see you first need to take the derivative of the exponent and just put again the argument in. So the outer derivative is just again this expression. So the first term here will just be det G, that just remains. That's from the most outer derivative. Then this trace will not, we can just take or write it again inside, because of course the derivative of a trace is still the trace. It's a linear function. We just take the whole thing inside. So we get here trace of, and then we still have to take the inner derivative, which is delta to the delta G of the logarithm of the matrix G. So that we still have to do. Now what's the, now it's really just a matter of calculating things. So we have the trace of this inner thing. The derivative of the logarithm is obviously 1 over g. So this is g, the inverse of g. And then we just have d to the dg. Now, yeah, actually, let me change here something. I tried to actually simplify it, but this didn't work. What I will do is the following. I will do the same that I did here at the beginning, where I said if we take the variation of something, then we can also again multiply it with this delta g. So that just would mean in this functional thing that thing. So we kind of multiply everything again with the thing we vary. So I'll just put that here in color so that you see what I change. I put here delta g again in, and then I have to do that here as well, delta g. And then what I'm left with is just here the delta g. But these are all matrices. So remember that, of course, if we're talking about matrices. And I could now, therefore, again return to the index notation. So what is this thing within the trace? Within the trace is the multiplication between two matrices, but if I take the trace of a multiplication between two matrices, then this really means that I essentially sum over both indices of the matrix. So the inverse matrix of G is by definition Gij with upper indices. Remember, that's how we defined G with upper indices as the inverse of G. And then the delta Gij has just indices downstairs, and because of the multiplication of and the trace, we have the same indices on both sides. So now we understand this thing here. Actually, in the script, and maybe also for the future, I will just call this delta of det G. So delta of det G is the same as is the short form of taking the derivative to G and again multiplied with the variation of G. Now, using exactly this short form, I can now do the next step and say, what is now the square root of the determinant of G? Now, the square root of the determinant of G, again, just apply the usual chain rule. So we first have to take the derivative of the determinant, which is this. And then the inner derivation is just the derivation of the determinant of G. But now I'll do here something. I'll write here just determinant of G without an absolute value. So remember that what I wrote on the left-hand side, this is really the determinant of G and then taking the absolute value. That was just a short form. You only write the absolute value, but the understanding is always take the determinant and then the absolute value. Now we are in space-time, and in space-time, the metric always has determinant -1. So this thing will just be minus determinant of G. And now I just absorb this minus here. Okay, now we can combine everything, or everything, at least we can combine it with the step we did above, namely this calculation. We already know what the determinant of the delta of the determinant of G is. And you see we have again here a multiplication with det G. Here we have 1 over square root of det G. So I could now again, yeah, let's just write here det G. And now I put the minus again inside here. I can, of course, do that. And on the bottom, I write this out explicit. It's the determinant of minus G. That's the same as taking the absolute value of G because of this minus sign. And here, for this part, I already now extracted this. this is what I wrote as det minus g and absorbing the minus, I still have to put this term here, this multiplication at the end, which is just, yeah, let's just copy it. It's gij times delta gij. And obviously, I can simplify this prefactor. This prefactor is just, again, the square root of the determinant of minus g, which I can again write as square root of g, determinant absolute value, and then I get this expression. Okay, you see, it's quite some work to do all that, but now at least we have done something, namely we have now an understanding of what this term that we, at least of one term that appears here. But that's not so much, you have only one part of this. At some point this will appear, the determinant of square root of g. Okay, so we have to continue working. We also have here an inverse metric, as you see, and here as well. So we also need to find out what does it mean to take the variation of the inverse metric with respect to the metric. But that's actually quite easy. So let's just note some other thing. So it's always useful to note a few things, namely that the variation of gmn times gmn, the inverse times the metric, this gives, of course, the identity. So that thing here is just the identity. If I take the variation of the identity with respect to g, then I get 0. But now I can again apply the chain rule. And the chain rule tells me that this is essentially just, yeah, let's first apply the derivative to the first term. I have g mn delta g mn, and then plus g mn with indices upstairs times delta g mn with indices downstairs. And this just therefore tells me that I can always swap the delta between the g's, between the g and the inverse. I just get an inverse sign. So this is essentially equal to minus that. And I will use that several times in what follows. So remember that. So now we can really do we can rewrite already the term above. So if you go back here, we did the variation for the square root of delta g. For later use, I want to turn this into a delta g with indices upstairs, which I can now do using this rule here that we just derived by just taking the delta to the front and changing the sign. So what this means is that we have delta square root of g, the variation of the absolute value of the determinant of g is therefore minus, oh, I think I forgot something, and no one notified me. This is a bit worrying. So there was an error here. Namely, here I took a derivative of the square root, and obviously if I take a derivative of a square root, I'll get, I think, a 1/2. So I guess there must be a 1/2 here. For some reason I don't have this in my notes, but I think it should be really a 1/2 here, because just of the square root with respect to which I took the derivative. So I also have it here. And then we get this, as I said, I can now exchange upper and lower indices, and for later use I will call them, instead of I and j, just m and n. Of course, indices I sum over can always be relabeled as long as I do that consistently with all the indices the same. Okay, now given that, we finally have an expression for what appears here as the variation in 1. So we have here this bracket which consists of gij times the square root of the determinant of g. So we essentially have an expression of this form, gij, using this abbreviation that I introduced, this thing. Now again, applying the product rule, this is just delta G ij, and then the whole thing times the determinant. I don't think I need a bracket here. And then minus 1/2 G and then G ij. Oh no. Yeah, so that's still that part here. And then times the derivative, which is this whole part. I already put the minus 1/2 in, which is giving me Gmn. So I'll just copy what I got above, times delta Gmn with upstairs indices. Okay, I hope everything is clear so far, but I realize I'm far over time for the break, and I think I need a break after this first part of the calculation. So let's make a relatively short break, maybe until 5. I hope I can therefore stop a bit earlier and compensate for the short break. And then I will just continue with the calculation. Okay, so are there any questions you would like to address me during the break? For those who want to briefly leave, I will continue exactly at 5 o'clock. Oh, I saw that. Okay, I see there was something about the minus sign in the chat. Did I lose a minus sign here? So let's see. Okay, so there's a question in the chat, which I think concerns here the sign here, which doesn't appear here. Okay, the reasoning here was that the minus sign, so I think it's correct because this minus sign, which still is there, so let me make it appear a bit more clearly. So there is a minus sign in the first term. This minus sign I've now put into that term here, because you see what I actually would, if I take this part here, so the derivative of that G, this gives this. So I have to insert this whole thing here. But when I insert this whole thing, I can of course also put a minus somewhere, and I put this minus here in front of the G so that it appears here. So in other words, this minus here has now moved to here. And then I just remind you that the determinant of minus G is equivalent to just the determinant of the absolute value of G, because the determinant of the metric has a negative sign in a Lorentzian manifold in space-time, and therefore we indeed arrive here at this expression without the sign. However, there is then a sign change again here, because we used this rule that the sum of these two terms equals 0. So by changing essentially the delta here from the part which has lower indices to the part which has upper indices, we again pick up the sign. But as I said, I'm not very good at signs, so I hope this is not completely wrong. Okay, are there further questions? Okay, see there's one in the chat. It says, when we use the chain rule for functional derivatives, don't we need to add an extra integral with respect to the usual chain rule? For example, when computing delta det G. Okay, I'm not quite sure I understand why you think there should be an integral. So we are really just using, okay, maybe it's, I see what the problem is. I think what I did, okay, yes, that's a good, now I understand the question. The question is, obviously here I started with something where the variation is outside of the integral. What I did use to get from this line here to the next line, to this one, is not only the product rule, but I also used essentially the fact that we can usually exchange derivatives and integrals. Now again, this is of course something that is not true in general. You know that well if you paid attention in mathematics. But I mentioned maybe earlier that we are usually assuming that all functions we are considering are nicely behaved. And we would just in retrospect define whatever nicely behaved should mean in order for these things to work. Because physically we never have a problem. Physically, the functions are in all the regimes where we can potentially test them experimentally, always nicely behaved. Maybe not at the singularity of a black hole, but there we can also not test it. So there we just have to accept that we don't know what's going on. But that's the general idea. So we just exchange derivatives and integrals. And so this derivative here just was moved inside of the integral, assuming that we satisfy all the necessary continuity properties and so on, that would allow us to do that in a mathematically justified way. Now, there was also a question about why is the determinant of the metric negative? So remember that the metric G has the signature 1 minus 1 minus 1 minus 1, meaning that there is a basis in which the metric looks like this. And because the determinant is a basis, essentially basis independent. I mean, it's actually not, but the sign of the determinant is basis independent. And you see that obviously the determinant here is negative, so it has to be negative anyway. Of course, if we had just four-dimensional space, I think that was the question, then it would again be positive. But we don't have four-dimensional space, we have three-dimensional space-time. And what that means is exactly this. So what it means to talk about space-time rather than space means that we talk about the signature where the first entry has a different sign from the other ones. There are also different conventions, and of course with a different convention the whole thing may change. Note, however, that if I had the convention minus 1, 1, 1, 1, I would as well have the negative determinant. So the different conventions have no influence on the sign of the determinant. Okay, are there any other questions? Okay, if not, then I will now continue. It's 5 o'clock. So what did we do so far? So we essentially wanted to prove this variation claim. We wrote it using the product rule as a sum of two terms. And so far we just calculated explicitly this term here that appears in the integral. And we found that this term equals the expression that we see here on the screen. Now let's continue with the second one. So there is also a term here that we need to evaluate, which sounds a priori even more complicated because it's a variation of the curvature. And you know the curvature is by itself a rather complicated object. Nevertheless, there's no way around it, so we'll have to do it. So for 2, we first actually need to remember that the Ricci curvature is derived or is a trace of the Riemann curvature, which is an even more complicated object because it has 4 indices. So we consider the Riemann curvature. We have to do that. Okay, I think it was really Hilbert who made this calculation for the first time. And I think I have to admit that I would probably have given up at least at this point here, if I didn't know that the solution would be so nice at the end, when you have to take the variation of the Riemann curvature. So this is just an incredibly, I would say, yeah, I shouldn't say ugly object, but at least if I write it down in terms of coordinates, it is actually a rather ugly object. Namely, it's the following. So remember, the Riemann curvature can be expressed in terms of the gamma symbols. So I'll just write down this expression here. Maybe remember it first has, and of course I put the delta everywhere. So the delta is just the variation, and if I have a sum of terms, I can just take the delta inside of the sum. So the Riemann curvature consists of a sum of things, and one thing is the one I've already written down. A second one is this that I just wrote. Then there are a few more terms. There is also a term which consists of a product of gamma symbols, namely here, let's say m and then Rn times gamma Rij. Okay, then I have one more with a negative sign, and I need to take the variation of all of those. Because of course, if I vary a sum, I have to vary all terms of the sum, Rin. However, there's now an important observation we can make. If you look at the derivative here, it's a product rule, so we will always have terms of the form here, of something of the form gamma times delta gamma, and so on. Now remember also that we always have normal coordinates. At any point in space, we have normal coordinates. So if you, for the moment, just say, let's just look at the variation of delta r at one point. And if you understand it at one point, then of course we understand it everywhere. Then we could say, let's just evaluate this whole thing in normal coordinates at that point. So think for the moment of this variation delta of just evaluating it at the fixed point. And then because I get terms like this, and because in normal coordinates the gammas are always 0, then also gamma times the delta gamma is 0. Delta gamma is not necessarily 0. Delta gamma involves the variation. Because I vary the metric, the gammas will change. But let's just suppose I take normal coordinates for which are normal with respect to the gammas where I have essentially where I start the variation. And then because I have these products, gamma times delta gamma, all these terms go away. So that, of course, simplifies our life. So you can just scratch that. Maybe I'll write down in normal coordinates. But of course, we are free to choose whatever coordinates we like if we do a calculation. Of course, when we define new things, we have to make sure that the definitions are coordinate independent, but that's not an issue here. All these things we are talking about are already well-defined tensors, and we're just now working with them. So hence we can write the following. We can say that the Ricci tensor, which is the contraction of the Riemann curvature, so remember it's essentially taking an index upstairs or summing over the index upstairs with the second index downstairs. That was the definition. We just keep the two terms here. So I just now copy these two terms, but I sum over m identified with n. So what I get is delta m ij semicolon, or not semicolon, comma m, that's not a semicolon, it's a comma, that's the derivative, as you remember, and delta gamma n I n comma j. So I should now really remind you that these commas mean partial derivatives. Now there is one more observation we can make. I told you many times that the gammas are symbols which cannot be seen as the components of a tensor. However, delta gammas, so for example, delta gamma ij are components of a tensor. So I can define a tensor that essentially has components delta gamma mij. I will just tell you why in a minute, but let's for the moment just assume this is the case. So we therefore can think of these objects here as tensors of which I take the derivatives. But I'm in normal coordinates, and you know, if I take the partial derivative in normal coordinates, then it's the same as taking the covariant derivative. And maybe you also remember that we wrote the covariant derivative in terms of a semicolon instead of a comma. And so what I can do therefore is just to write here ij semicolon m, and the same here for the second term in semicolon j. Now, why is it true that delta mij are tensors? So remember, a tensor, or the components of a tensor, have to transform in a particular way. And I think I gave this example quite some time ago, where I said, if you change basis, then the gamma symbols transform as follows. So I'll write this down, dxr, dx tilde I, and dxs, dx tilde j, gamma n rs. So that would be the transformation rule for a tensor, but then the gamma symbols have an additional term, namely the second derivative of dx tilde n derived with respect to xi and xj. Now, yeah, this term is really the reason why they are not components of a tensor. But suppose now that we take the difference between two gammas. Now, if you take the difference between two gammas, then what we get is still the I mean, here, of course, I can just take the difference here. They will just commute with this. Or, okay, let me maybe do it more explicitly. Let's just suppose I have another gamma. So gamma tilde here is the same gamma as that, just in different coordinates. But let's now suppose I really have a different gamma. So maybe I indicate that, okay, there are already many indices and so on. Let's just say we have it in different colors. So the orange gamma is a different one from the blue one. Then, of course, I have the same transformation rule for the orange gamma. But if I now take the difference between two gammas, and I write down the difference in the tilde coordinates, then, of course, that's the difference of the right-hand side. What's the difference of the right-hand side? It's, again, this whole transformation, dxn and so on. I'll not copy everything. And then the difference, of course, of the blue gamma with the orange gamma, which is the delta gamma. Just consider the delta gamma to be the difference between the two. But look what happens with this last term. The last term for the blue gamma and for the orange gamma is the same, because it actually doesn't depend on gamma. It just depends on how I transform coordinates, or on the two coordinate systems. So the difference between these two terms just gives 0. And what I'm left with is this transformation rule here, which is the transformation rule of a tensor. So therefore, delta gammas transform as tensors, which justify the fact that I can here put semicolons, which mean that they're contra or covariant derivatives. Okay, I'm aware that today's lecture is quite calculation intensive. I'm sorry about that, but this is just how it is. I mean, we have to do this calculation at some point. It's essentially an integral part of GR. Or at least the understanding of where the Einstein equations come from. So let's now look at the term that we have in expression 2 above. So on the right-hand side, we still have this thing that we want to essentially express here. And you see there is not only the variation of R coming up, but it's the variation of R times Gij. So let's look at this thing here as well. Remember that the fact that I just write here a delta is just a short form for taking the derivative with respect to g and then again multiplying with g, with delta g. So what's this? Okay, I think I need some space here. Oh no, okay, actually we have it almost. So this thing is actually easy. It's just, we have already delta Rij here. So let me show it here on the right hand side. So we have an expression for delta Rij. We are just multiplying it with Gij. So that's pretty easy. So I'll just write this down. So it's Gij times the first term that you see here, which is that one, times delta gamma Nij. And now what I'm doing, I would now have to put the semicolon n, but I'm just putting the semicolon here outside of the bracket, which means that the derivative is a derivative that acts on the whole product. So it acts on this part here, but it also acts on this part. But this is the same as just taking the derivative only of the second expression, because note that the covariant derivative or that the metric is zero, or okay, that the covariant derivative of the metric is zero, because the metric is invariant under parallel transport. And therefore, I can as well just take the covariant derivative of the whole product here, rather than only this part. And this was actually this would not be true if we here had only a comma. So this is why we require the covariant derivative, because the partial derivative of the metric may be non-trivial, but the covariant derivative of the metric is always zero. Okay, we have this, and then we have, of course, the second expression, which looks almost the same, Gij delta. Now I take this thing here, NIM, okay, delta gamma NIM. And the whole thing, again, the same trick, I take the derivative with respect to j. Okay, this is a bit unfortunate because I would like to just take one big covariant derivative, so I need to relabel things a bit. So let me just do that. Let's copy the first term. And then for the second term, I just relabel the index j with an n. Of course, I can do that because there's a summation over n. That allows me to do it, but there was also an n appearing here. So I'm essentially exchanging n and j in the notation. And because both are summation indices, I'm perfectly allowed to do that. And then the expression looks like this. Okay, so what we have is a covariant derivative of a kind of ugly expression here. But now we will actually not have to worry about this expression in detail. The only thing we have to note is that this expression here is at the end just a vector, which I could call Wm. Why is this the case? So note that this here, this Gij, is a tensor, of course. This is also a tensor, as I just argued. And this is, the whole thing is essentially a contraction of a tensor, because I contract these indices Ij with Ij. And the only index that is left is an n. So this thing would be a 1-0 tensor, which is of course a vector. And the same for the second term. And of course the difference between two vectors is again a vector. So what we arrived at with this shorthand notation is that the whole thing is just some vector and then the covariant derivative of it and traced over the whole thing. So this index m is the same as here. That's this n here coincides with that. And now this should ring a bell, because you know that, and you probably remember that we defined the divergence in that way. And that will be useful for what follows. So let's now just summarize the whole calculation. Now we are close to the end of this very long calculation. So what we wanted to do, remember, is to essentially look at the variation of the action, of the Einstein-Hilbert action. Now, the Einstein-Hilbert action can now be or this variation can now be written as follows. So I still have the prefactor and I have the integral. I need to go up a bit here on the right-hand side. So you see, hopefully here, this expression here that we decomposed into 1 and 2. And I'm now putting everything together. So I'm first writing 1. So first term consists of Rij, and then we evaluated the rest. So what was the rest? We found that this expression here is equal to, so let's see where it is equal to that thing here. So let's just write it down. Oh, okay. Yes, let's see. Yes, it is that. Okay, so I'll have to first copy that, or at this point I have to copy this expression into the integral, which gives the following. So let's just do that. I get a delta Gij, and then the square root of the determinant of the metric. And then I write the second term separately, minus 1/2, so there's a minus 1/2. I put the Rij again from before. I don't want to take it out of the bracket. And then I also have the Gij. So up to this point, I just took the terms that are before the derivative. And then I have to scroll up again for a moment. Sorry about that. So far I put again the term here Rij first, and now comes the whole derivative, and this whole derivative here is of course, as we said before, the expression here, which I'm now inserting. So we have a Gij, we also have a square root again of the metric, of the determinant of the metric. We also have a Gmn, and we have a delta Gmn. Okay, I start to run out of space. I think it almost works. So I still need to put the delta Gmn. And then I've really accommodated everything from the first part of this long equation. Now we still have to take care of the second part. So the second part was also in the integral. So let's suppose the integral continues here, plus, and here we just found that it's essentially this vector m, and then the part that we didn't, and that was this thing, and then we still have that little square root of g. Note that this Wmn included already the Gij. So we already have taken this into account. So the only thing that is left here is really the square root of the determinant of g again, and then we have the whole integration, which is dx4. Okay, now we have a long integral to solve, but it's not as bad. Note that we can easily rewrite it and bring it into a form which already looks extremely promising. So first of all, we have this term Rij, and I'll take the delta Gij out of the bracket later. So let's just immediately continue with the second part, which is an Rij Gij. But what's this? This is just the Ricci scalar. So I can just put here the Ricci scalar, and then we still have somewhere a G Mn. I may relabel, yeah, okay. Let's again relabel things. So here I have an Mn and again an Mn. Let's relabel them by Ij. I think I'm allowed to do that, and this is of course useful because here I have a delta Gij. So I want to label this in the same way so that I can just take the delta Gij out of the whole integral. So think of this summation here as gij times gij. And then this looks like gij here. And then out of the bracket, I can now write just jointly the delta eij. And I still have the square root of this. But now remember, this was the volume form. So I can just return to writing the volume form. And this makes the whole thing coordinate independent. Now I still need to take care of the second integral. But here I said this w is essentially the divergence of w times the volume form. Remember, that was also the definition of the divergence. So this thing is equal to the divergence times the volume form. Now, what's the divergence? The divergence, remember, was defined as the exterior derivative of iota of the vector field applied to the volume form. And now this is nice, because what is an integral applied to an exterior derivative? That's, of course, the same as the integral over the boundary of u times the thing that is inside of the exterior derivative, which is something like this. But notice now that this is just there for a boundary term. So if we change things only in the interior, and here I'm a bit, let's say now, careless. Let's just suppose for some reason we can do that. We just change the delta gij in the interior of u and not at the boundary. There are some problems with that, but we will not address them for the moment. Let's just suppose we can do it. Then, of course, this expression here equals 0 whenever, and because this has to be 0 for all variations of delta j, it equals 0 whenever this thing here is 0. So, in other words, what we found is that this equals 0 for all delta gij if and only if the bracket is 0. The bracket is rij minus 1/2 rgij. And that's, of course, exactly the vacuum Einstein field equation. Okay, that was really a longer thing. I think it was the longest calculation of this course, but it was probably worth it, because what we got as a result is what Einstein postulated as the fundamental equations that determine the geometry of space-time, at least in vacuum. Are there any questions so far? So I'm aware of the fact that if you have never seen this calculation before, you may need to return to it and go through it again step by step and see whether you're really sure all these individual let's say transformations that I've used really work and are really justified. And if questions come up, that then of course I'm happy to answer them next time, for example, and also certainly the teaching assistants will be happy to answer them. Note that there's also a question and answer session, by the way, which is also announced on Moodle. Okay, so now this is still not the full story, because we have only the vacuum equations. Things will not get more complicated now if we go to matter, and actually we now encounter the first advantage of thinking of action principles. So note that what we started off with was to say, let's just take this action and vary this action. Now, if we look at matter again, which is of course something we wanted to do, then the idea is we just add a matter term to the action. So we don't have to change what we did so far. The whole calculation is still useful. We just add an additional term. So this is, of course, now again a postulate, if you want. So this is not something I will derive. But let's just see what is a general matter term. So general matter term is something that is also an action over, in general, some region U, but it's an action that depends not only on the metric G, but in general also by of some field that describes the matter. So let's maybe say with matter given or modeled by a field psi. Now this psi will can, for example, be the electromagnetic field. I think I told you that matter in general includes radiation matter, and radiation matter is really the matter that consists of the electric and the magnetic field. So one special case will be to say, let's just here take the action, an action term which includes the electromagnetic field. But in the general form, we will just write down a so-called Lagrangian density, which depends on the metric, on this field, and potentially on derivatives of the field. And then, of course, to integrate the scalar, or to integrate, yeah, okay, depends on whether I call it density or not. So if I could either include this term here into L or not, let me now consider this as a scalar, so it's in there, that sense, not a density, and then I mean it's a density with respect to the volume, but not a density with respect to the coordinates, if I write it like that. But this is a scalar, and then I multiply it with a volume form. So the idea is that whatever matter we have, and this can now differ from the type of matter, we will have some additional term in the action of this form. And this really depends on the matter. That's not a matter of GR to determine how this L looks like. Of course, GR should help them to figure out what it means for the Einstein field equations, but that's, for example, a matter of electromagnetism or of any other theory of matter. Maybe if you have a theory of particles, then this gives you a Lagrangian, and you put that Lagrangian here into that thing. So that's kind of the input from other theories that enter Einstein's field theory. Now, one thing you can do is, I mean, note that on in the Einstein field equations on the right-hand side, we had the energy momentum tensor. It now turns out that the energy momentum tensor can generally, it could even be defined in terms of an action principle. So rather than just defining it as I did it last time, we essentially postulated how it looks like based on considerations of point particles. But now, of course, if you look at electromagnetism, we don't have point particles, we have some action. And the question is, how does then the electromagnetic field tensor look like? And what one can do is to just define it in a general manner. So the general definition of the energy momentum tensor via action is the following. One just says that if I vary with respect to G, so if I take the variation of this, whatever action you give me, so for example, you give me the action of electromagnetism, which is some function S that depends on G and the field, then, and I vary it with respect to G, then the electromagnetic, or the energy momentum tensor should be the tensor which satisfies this integral equality. Okay, this looks now a bit strange, but I could just, I define T in terms of an integral equality. Why is this a useful definition? I mean, so far it's just a definition. I can, of course, define whatever I like. But it turns out that this is, if I use this definition, I will exactly get back the Einstein field equation. So that's already a first motivation for the definition. So let's see why this is the case. So let's suppose that we just accept this definition, and now we vary everything. So we take now the variation with respect to the metric of the action that we defined before. So that should be the Einstein-Hilbert action. And so that's some matter action, which, as I said, depends on whatever matter you're considering. And now I just add the other action, the matter action, here to that. So again, that's the matter action. And now I could, of course, add several types of matter. I could have one term of electromagnetic matter, then here write plus and another SU of particle matter, and maybe you detect even a new type of matter, dark matter. You put an additional term there, and so on. So at the end, what you postulate in physics, that's kind of the input into the theory, is all phrased in terms of actions. And now the idea is that whatever the equations are, they should come out by varying this action. And if you vary it with respect to the metric, then you should get the Einstein field equations. And that's now very easily seen to be the case. It's almost true by definition, because remember that if we vary this first thing, we get what we calculated in just previously. I mean, that was exactly the calculation we have essentially done here. Remember, we calculated the variation of u, and what we got is 1 over 16 pi gn, and then the integral over u of rij minus 1/2 rgij, and I'll now just drop the boundary terms. And then we have the other action, but the other action is just defined in such a way that it gives this term. So here I just have to read off this. I vary this action, and what I get is an additional term. So let me just include it here. The additional term is just minus 1/2 Tij, and then I can close the bracket, and outside of the bracket I still need to put, of course, the variation delta Gij, and I also need to put the volume form omega g, otherwise this integral doesn't make sense. So I put this. And okay, this should be 0. That's what the action principle tells us. And of course, this is satisfied if, so this should hold for all delta Gij's. So for however I vary, in whatever direction I vary the metric, I want that this is true. So therefore, again, this bracket has to be 0. And now you see, if I multiply the whole equation with 16 pi gn, I get exactly the Einstein field equations. Rij minus 1/2 rgij, and of course I can take the t on the other side to make everything look really as we had it before, equal to Tgij. Okay, you could now say, okay, this is just cheating. I just defined this whole thing exactly the way that the right thing comes out. However, it's not cheating. There's a very deep insight we can get exactly from this consideration. And that's the last thing I want to do for today. So let's maybe make this, to explain this insight, let me consider a concrete matter action. So as I said, an example is the electromagnetic field. So that's an example of a matter field. So in this case, the Lagrangian density is given by a field which is the A field. So the A field is this four-dimensional field that you know from electromagnetism. And of course, the Lagrangian may also depend on derivatives of A. So actually, let me write down A is really in components. So let's say A is a vector field, and the vector field has components, and it corresponds in a normal basis to what you would in electrodynamics consider the electrodynamic potential. That's A0, and all the other terms are just the corresponding terms of the three vector A that you know from electrodynamics, but with a minus sign. So one is minus AX. Underline should indicate it's the 3 vector from electrodynamics. Okay, that's now electrodynamics, and I don't want to go into electrodynamics too deeply now, but what you should know, electrodynamics is described by such a field. And now I can say, let's define a Lagrangian based on this field. And this Lagrangian I could define as, okay, it's useful to actually introduce an abbreviation, F, which should be the exterior derivative of A. So F is, of course, the electromagnetic field tensor. That's a 0-2 tensor. And you may have seen in electrodynamics, at least if you took electrodynamics with me last spring, that we can write the electromagnetic field tensor F as an exterior derivative of the 4-vector A. So for the moment, this is just an abbreviation. You don't need to know what F really is in terms of the electric and magnetic field. It's just something that derives from dA. And I could as well just always write dA whenever there is F. And now the Lagrangian density is given by Fij times Fnn with a prefactor, which is essentially a convention, Gim Gjn. Okay, so that's now a concrete action that I would insert here when I said, okay, here we have general action, I would just insert that in this equation. So in other words, if I have a situation where I only want to consider gravity and electromagnetism, then the relevant equation is this equation here, where SU is the Einstein-Hilbert action, and this second thing is exactly an expression of this formula, an integral over a Lagrangian, which is this Lagrangian here. So that's essentially then the Einstein-Maxwell equations are the equations that come out of that. Now you may wonder, where are now the Maxwell equations? Note that what this Lagrangian defines is an action, SU, that depends on G and on the electromagnetic field A, and, okay, of course, also derivatives of it, which I'm not going to write here. Now, when you look at the expression that I wrote here on the right-hand side, which give the Einstein field equations, what I did is to take the derivative with respect to the metric. But this does not only depend on the metric, but also on A. So I could also say, look at the derivation of this with respect to A and ask myself, what does this give? So this would be a possible way to write this. What this gives are exactly the Maxwell equation. I will now not show these derivations. This derivation is analogous to the corresponding derivation in electrodynamics. It's given in the lecture notes if you're interested. But the point is that I have the same action. And if I now take the very same action, that's just writing what I told you before, and I take the Einstein-Hilbert action and add this action to it, then I get the Einstein equations. That's what we saw before. But this is now remarkable because we get two completely different equations, namely the Maxwell equations, which are the equations from electrodynamics, and the Einstein field equations with, essentially the part here. I mean, this part is essentially the matter part of the Einstein field equations, the T. We get that part as well as the Maxwell equations from this very same Lagrangian, from the same action that we defined. So this means that there is de facto only one interaction. There is one thing that describes how electromagnetism interacts with the geometry of space-time. And this interaction is completely described by this Lagrangian. Now, this interaction has two implications. One implication is the implication that tells us how does the electromagnetic field evolve in general in a curved space-time? I mean, maybe I should write here, these are the Maxwell equations in curved space-time that we get. So this derivative here, or this variation tells us how does the geometry influence the electromagnetic waves? How do the electromagnetic waves propagate in a given geometry? That's analogous to what we did when we studied particles, when we said we have one term which is like the Lorentz force, it's not the gravitational force. It tells us how does gravity or the geometry of space-time act on test particles. That was one thing. And then I said it's a completely different thing to say how does matter do the opposite, namely influence the geometry. So we have these two directions. We have the geometry and we have matter. And so far, saying how the geometry influences matter was a completely different business from saying how matter influences the geometry. But what we have now found is that they're both directions come out of the same Lagrangian. This direction here is the direction that is covered by the Maxwell equations in curved space-time. If I have the Maxwell equations in curved space-time, I know how electromagnetic fields and therefore radiation and light propagates in curved space-time, and therefore how it depends on gravity. It will explain, for example, how light is deflected by gravitational field and all that. So these are all things I can view as the geometry influences matter. But then the same thing told us what this thing is, which are the Einstein equations, and the Einstein equations tell us how matter influences the geometry. In the case of the electromagnetic field, we would of course have to calculate that. So we would have to do a calculation where we say, what's now really this term? So this was very abstract here. We just said it's some term t, but now we have a concrete action and we can actually calculate this. So we could, in principle, now say, what's now this term? We'll not do it now. I think there's not enough time. But in principle, we could calculate this term. And okay, if you like, I could still do it on Thursday. But let me just give you the result. The result of the calculation is, okay, I've written it up somewhere here. So the result of the calculation is, okay, there's a long calculation, not as long as the one we did today. So, but still, one needs to work a bit to get it. And then one gets an integral still. The integral involves the f, which is an abbreviation of dA. It has here m, a, f, mb. Okay, the m is just a summation index. Actually, there's a minus sign here, plus 1/4 f m n f m n GAB. Yeah, actually, the calculation is not that long. Let me just say calculation. This has the advantage that I need less space here and can shift the whole thing over. So there's some calculation you have to do. And okay, the whole thing is in a bracket, and you still need to put the volume form somewhere. So there's an integration, and then there is somewhere a variation, delta G AB, and then there's the volume form omega G. Now compare this to what we defined as T. So you see this thing here is what I calculated now in the concrete case. I should write here, this is times delta G. So this is, excuse me, this was not, okay, I think I made a mistake. I wanted to say, what is this if I take the derivative of G? So I wanted to do this thing here, not the A part, the Einstein equation. So I take the derivative to G, do a calculation and get this expression for the integral. But if you compare it with this expression here, then generically, what I write here in the inside of the integral in the square bracket corresponds to the Tij, more precisely to minus 1/2 Tij. So by definition, this is minus 1/2 TAB. And this was also something I just postulated last time. At the end of the Thursday lecture last week, I told you for an electromagnetic field that the concrete energy momentum tensor is just this. And you can look it up. I think it's here. This was from last time. Okay, where is it? I think I wrote it down somewhere. Ah, yes, it's actually here. So it's this thing. That's exactly what comes out now of a calculation. Okay, let me briefly summarize. I know I'm over time, but let me spend 2 minutes to summarize what we did today, because that was really important as a conceptual thing. And I don't want that this is all drawn in the long calculation that I did today. Okay, the goal of the lecture was to argue that there is we don't need to postulate the Einstein field equations in the form I did it last Thursday. And so far we haven't taken care of the cosmological constant. Forget it for the moment, but it would just correspond to an additional term in the action. It's actually an additional, very simple term. It's just an integration over the volume form times the constant, essentially. So that's the only thing I would have to add to the action to also retrieve this term. Now, what we said is that, or what we now saw, is that we can indeed get these equations by an action principle. And more precisely, it's the addition of several actions, namely the one I've written down at the very end here. It's essentially this action principle here. The first term is a pure geometric term. This was the term that is called the Einstein-Hilbert action and just includes an integration over the Ricci scalar. So that we always have as a term in the action. Then the second term really depends on the type of matter we want to study. I gave you an example. In the electromagnetic field, it is the term which is given as an integration over a Lagrangian, where the Lagrangian is given in terms of the A, or the electromagnetic field tensor, and you have to vary it with respect to A to get the Maxwell equations usually. But now we don't want to get the Maxwell equations, but we are of course happy that with the very same action we also can get the Maxwell equation. We want to get the Einstein field equation, so we take this action that is well known from electrodynamics. That's not something new to relativity. The only thing that is new is that we realize actually it also depends on G. Of course, in electrodynamics, we would not have written explicitly what the G is in the definition of the Lagrangian. You would just have summed over it. But essentially, the G's have to be there to make this thing a valid scalar. And there's only essentially one choice to do it. So if you take the electromagnetic field equations, go to normal coordinates, and then consider that as the right thing, then you will get this expression with the right G's and so on. So we just took this and this electromagnetic action and said, let's vary it with respect to G. And then by varying this, we got precisely the Einstein field equations for matter in the case of electromagnetic matter. And that was the last, so what I've shown as a calculation was the variation of the first term. The variation of the last term I just claimed has the right form, but this is also given in the lecture notes. And in case you ask me to do it, I'm also happy to do it on the Thursday lecture. Otherwise, I would like on Thursday to tell you a bit about gravitational waves, which I will probably anyway do, but I'm happy to start the lecture by giving you additional explanations on this calculation. Otherwise, you can find it in the lecture notes. Okay, that's it for today. Thanks for staying so long.